This lesson will cover different types of acceleration and how to calculate the average acceleration of a moving object. Up until this point, we have been dealing with objects that are moving at a constant velocity, meaning that the object is moving at the same velocity for the entirety of its motion, and it's moving the same distance per unit of time. Objects don't always move with the same speed the entirety of their motion. Some objects even have to change their speed from resting to the desired speed. Acceleration measures that rate of change in velocity, meaning velocity of an object is changing, and acceleration tells us how much that object is changing its velocity per unit of time. Remember, velocity is a vector. It deals with magnitude and direction. So anytime the direction of an object is changing, the velocity is changing. So it is then accelerating. Acceleration is also considered to be a vector and has its own direction. These are the different types of acceleration an object could be experiencing. It could be speeding up, slowing down, or even changing direction. Any change in velocity is considered to be acceleration. We calculate change in velocity by subtracting initial velocity from the final velocity. Here is the whole equation for average acceleration, the change in velocity over the change in time. Something I want to point out to you really quickly is the symbol for initial velocity right here is different from the initial velocity symbol right here. V sub naught, or V sub 0, means the exact same thing as V sub I. They are two different symbols that mean the exact same thing. You're going to see this equation written differently from time to time using VI or VO. They mean the exact same thing. Don't freak out. I will be using this symbol when I'm working out these problems. The units for acceleration are meters per second squared, typically, or they can be something else depending on the units we are using for whatever we are measuring. You can see where we got our base units if I plug in the formula right next to them. We measure velocity in meters per second, and time is typically measured in seconds. When I rearrange those units to make them a little simpler, I end up with meters per second squared. Acceleration is a change in speed or direction. So here are a few examples of each. I could be experiencing a change in speed by speeding up or slowing down. I could be moving at a constant velocity, but my direction is changing. I would still be accelerating because my direction is changing, so therefore my velocity is changing. And I could be experiencing both at the same time. This can get a little tricky, a little confusing, because velocity and acceleration are both vectors and each have their own direction. A positive acceleration doesn't always mean I'm speeding up, and a negative acceleration doesn't always mean I'm decelerating. I have a trick that might help you when figuring out what an object's doing based on the signs of the velocity and acceleration vector. First, I want you to think about velocity. A positive or a negative velocity doesn't tell me anything other than the direction that the object is moving in. So when you see a velocity with a direction attached, just think of that as the direction of the movement, the direction the object is moving in, positive or negative direction. For acceleration, I want you to think of an object getting pushed. And acceleration is kind of like a push on an object. We'll get into why at a later unit. So when you think of acceleration, I want you to think of direction of a push. Something is pushing on the object, causing it to change its motion. Let's try a couple of examples. So let's say an object has a positive velocity. All that means is it's moving in the positive direction. If it has a positive acceleration, that means it feels a push in the positive direction. If I am moving in some direction and I receive a push in that same direction, it's going to cause me to speed up. And I'm still going to be moving in that same positive direction. If I'm moving in the negative direction, because I have a negative velocity, and I receive a push in that same negative direction, it's going to still cause me to speed up. But this time, I'm moving in the negative direction. Anytime my signs for velocity and acceleration are the same, that is going to mean that I am speeding up in whatever direction I'm traveling in. When they are opposite, it means something different. If I'm experiencing a positive velocity, that means I'm moving in the positive direction. But I receive a push in the opposite direction. Those are going to kind of work against each other, and I'm going to end up losing some velocity and slowing down in that same direction that I'm traveling in. If I'm moving in the negative direction and I receive a push in the opposite direction, again, those are going to be working against each other, and it's going to cause me to slow down in whatever direction I'm traveling in. Anytime the signs for velocity and acceleration are opposite, the object is going to be slowing down. Most of the time. Let's say you have a velocity, but no acceleration. That just means you're not going to be changing your velocity at all, and you're moving at a constant velocity. You could have no velocity, but you have some sort of acceleration. This usually means that you're speeding up from rest. So you're at rest, you're experiencing a push, but it hasn't quite caused you to move yet. But you might in the very next instance. If I have no velocity and no push causing me to want to change my velocity, I'm going to continue doing what I'm doing and stay at rest. Let's put all of this together and try a practice problem. I like to read an entire problem and picture the situation in my head. It's even helpful to draw a picture sometimes. Try to identify important pieces of information related to the motion of the object, what we're looking at. So a handball is hit towards a wall with a velocity of 13.7 meters per second in the forward direction. It returns with a velocity of 11.5 meters per second in the backward direction. If the time interval during which the ball is accelerated is 0.02 seconds, what is the handball's average acceleration? I like to identify what I'm actually looking for in these types of problems. Eventually, when you start playing with other equations, there is more than one equation with acceleration in it. It's helpful when you're trying to pick out a correct equation if you know what you're looking for. You can kind of work backwards from there. So I know I'm looking for acceleration, and this problem's a little tricky, so I'm going to draw a picture to maybe understand what's actually happening. A handball is hit towards a wall. So here's a wall, and it is moving in the forward direction at an initial velocity of 13.7 meters per second. It returns with a velocity, so it bounces off the wall and is going in the backwards direction at some other velocity, a velocity of 11.5 meters per second. I need to show that these velocities are occurring in opposite directions. The easiest way to do that with numbers is to make them different signs, positive and negative. If the time interval during which the ball is accelerated is 0.021 seconds, what is the handball's average acceleration? I'm looking for acceleration, so I'm going to see if I can use my average acceleration formula It looks like I have enough information to just plug in numbers and solve, so I'm going to do that. I need to make sure that I include my signs because this will affect my answer. Divided by 0.021 seconds. And when I plug all of this into my calculator, I end up getting negative 1,200 meters per second squared. It's a good idea to take a moment when you find an answer to make sure that it makes sense. For instance, I got a negative acceleration. Does that make sense here? Well, at first the ball was moving in the positive direction. According to, if I told you to think of acceleration as a push, that means it received a push in the negative direction, which seems to sort of make sense here. The wall pushed the ball in the opposite direction to make it travel backwards at the end. Let's try the next problem. In 1970, Don Garlits set what was then the world record for drag racing. With an average acceleration of 16.5 meters per second squared, Garlits started at rest and reached a speed of 386 kilometers per hour. How much time was needed for Garlits to reach his final speed? I am looking for time, and they gave me some useful information here. Acceleration is 16.5 meters per second squared. He started at rest, so I can assume his initial velocity was 0. And then his final velocity for this segment of his motion was 386 kilometers per hour. Something I noticed right off the bat, the units are different for all of these numbers. If I'm going to plug all of these numbers into the same equation, I want to make sure they're in the same units so everything cancels and I get an answer that doesn't have complicated units. So I'm going to choose to switch up to convert my final velocity units just to get them in my usual units of meters per second. I will, just kidding. Show my work here. And when I plug that into my calculator, my new converted final velocity ends up being 107.222 repeating forever meters per second. If this were my final answer, I would round this answer to 3 sig figs. And you should take note that this answer should have 3 sig figs. But if we use the rounded number in our equation, since this isn't our final answer, it will affect the number we get at the end. So we want to be sure to use the exact number in the equation that we're solving for. So let's look back at our average acceleration equation. It looks like we have enough information. We have information for everything but time, so we can solve for it. If you want, you can go ahead and plug in your numbers right here and rearrange the equation. But I am a fan of rearranging the equation first and plugging in numbers later. To me, that makes it easier to rearrange. I don't have to worry about moving around complicated numbers and units. I can just rearrange a few letters. And I would do that by flipping these two. And this would be the new rearranged version of the equation that I would plug all my numbers into. If you're not sure why I can do that, I can show you really quickly using a simpler equation. We'll use our velocity equation. Let's say I want to rearrange for time. I would do that by first getting time out of the denominator. It would cancel on this side, and I would get time times velocity equals delta x. I'm still wanting to get time by itself, so I'll divide both sides by velocity. And you'll notice this equation is the exact same as our original equation, but these two are flipped. This is a little shortcut you can use if you're trying to solve for something that's in the denominator and you just want a quick way to rearrange the equation. But I don't need to now. I have an equation I can use, and I'm just going to write that I'm putting in the exact number. You can write the shorter version if you'd like, but I'm trying to remember to use the exact whole unrounded number. Plug in all of my information and solve. And here, you can round to proper sig figs. So I should have 3 sig figs in this number, 3 sig figs in my bottom number, so I would round to 3 significant figures for my answer.